Welcome to the next module of the Securium Bootcamp. In this module, we will be discussing 101 concepts related to the most commonly encountered pitfalls and recommended best practices as related to the security of smart contracts on Ethereum. The Solidity language has evolved considerably in the last several years. There have been many features added, some of them removed. Security has been improved. In several cases, optimizations have been made, and as a result, there are many versions of Solidity that are available for projects and developers to choose from. At least one version is released every few months that makes some optimizations and fixes some bugs. A couple of breaking changes are introduced every year or so. As a result, the question is always about which version of the Solidity compiler to use for a particular project so that the best combination of features and security aspects are considered. The older compiler versions are time-tested, but they have bugs. The newer versions have the bug fixes, which is really good, but they may also have new bugs which have been undetected so far. The older versions have lesser features compared to the newer versions that have more features. Some of these are language level features that are visible syntactically. Some of them are semantic changes. Some of them are security features. Some of them are optimizations that are not very visible. As a result, the choice of an optimal version of the compiler for a particular project is always a tricky thing. And this has to take account not just the functionality, but also the security aspect. As a result, there is a trade-off to be made. There are risks as well as rewards. As of this point, many of the projects are transitioning to the Solidity version 0.8.0 and beyond, because among other things, this version has introduced default arithmetic checks for underflow and overflows. So these aspects of security and functionality and the range of choices available across the various Solidity compiler versions have to be kept in mind when determining which version to use for a particular project. Recall that Solidity supports the concept of Pragma directives, and one of them is related to the Solidity compiler version that can be used with the smart contract. There are many aspects related to that Pragma directive, but the one that is relevant from a security perspective is the concept of that Pragma being unlocked or floating. And what this means is that in that Pragma directive that specifies the compiler version, if the caret symbol is used, then it is referred to as being unlocked. And what this means is that the use of this caret symbol specifies that any compiler version, starting from the one specified in that Pragma directive, all the way to the end of that breaking version, can be used to compile the smart contract. As an example, if the Pragma directive is caret 0.8.0, it means that any compiler version from 0.8.0 all the way to the last version in the 0.8.z range can be used according to this Pragma for compiling the smart contract. And why this becomes interesting from a security perspective is that the use of such an unlocked or floating Pragma allows one Solidity compiler version to be used for testing, but potentially a different one that is used for compiling the contracts while being deployed. And this aspect of using a different version for testing and deployment is risky from a security perspective, because one could test with a totally different set of compiler features and security checks, and the newer version or a different version that is used for deployment may support a different set of features and a different set of security checks. So this mismatch between testing and deployment is allowed by the use of this unlock pragma and hence is not recommended to be used. So what is recommended is to lock the pragma by not using the caret symbol in that pragma directive. And this will enforce that the same compiler version is used for testing as well as for deployment. Another security aspect related to the use of the Solidity compiler pragma in contracts is the use of different pragmas across different contracts. Recall that the pragma applies only to the contract where it is used. So if there are different multiple contracts that are used within a single project, then each one of them could have a different pragma specifying a different compiler version. And the reason why this is not recommended is because these different compiler versions, like we just discussed, can have different bugs, different bug fixes, different features, and even different security checks across the versions. And this will result in different components of the application having different security properties, which is not desirable. So from a security perspective, what is recommended is to use the same pragma across all the different contracts that form that smart contract application. This will result in all of them having the same set of bugs, features, and security checks, which can be accounted for while one is testing that smart contract application. Access control is perhaps the most significant and fundamental aspect of security. And when it comes to smart contracts, what it means is access to functions. Recall that functions can have different visibility, and public and external functions are those that can be called by any user interacting with the smart contracts. So from an access control perspective, we need to make sure that the right set of addresses can call these functions. And it might be okay for anyone to access these functions, any address to access this function, or it might be required only for the owner to access this, or there could be an extensive role-based access control that is desirable as well. This means that when we are reviewing smart contracts for security, we need to make sure that the right access control is enforced by the use of the correct modifiers, that make sure that the correct checks are enforced on the different sets of addresses used with the smart contract, because any of these missing checks, either missing modifiers or the use of incorrect addresses or even the access control specification, might allow attackers to control critical logic that is executed within some of these critical functions. Smart contracts typically manage a significant amount of funds related to the amount of Ether or the ERC20 tokens that they hold and manage in different ways for different users. So they have different functionality for users to deposit these funds, and similarly they have different mechanisms for users to withdraw their funds. These withdrawal functions need to be protected from an access control perspective. And what this means is that if these withdraw functions are unprotected, that's if they are public and external and they do not have the right access control enforced on the different addresses via checks implemented within the modifiers applied on these functions, then it may let attackers call these unprotected withdraw functions and withdraw Ether or ERC20 tokens that belong to other users. And this unauthorized withdrawal leads to loss of funds for the users and loss of funds for the protocol itself. So in this context of withdrawal of funds, access control again becomes really important, and the security checks have to make sure that the right access control is applied with respect to the different addresses or different modifiers on these withdrawal The use of the self-destruct primitive is really critical and dangerous from a security perspective. Recall that self-destruct is an EVM instruction that is further supported by a Solidity primitive, which when used within a smart contract destroys or kills that contract and transfers all its ether balance to the specified recipient address. So from a security perspective, any smart contract that uses self-destruct within a particular function needs to protect access to that function, because if not, an user can mistakenly call that function, or an attacker can intentionally call that function to kill that contract and really remove its existence thereafter. This means that from a security perspective, unauthorized calls to functions within smart contracts that may use the self-destruct primitive should be prevented so that the contract does not get killed intentionally or mistakenly. Access control to such functions again becomes really critical to make sure that only authorized users may call such functions. And at a high level, even the use of self-destruct is considered as being very risky and dangerous from a security perspective. Modifiers in Solidity smart contracts are typically used to implement different kinds of security checks, access control checks, or accounting checks on fund balances, and so on. Such modifiers should not have any side effects. They should not be making any state changes to the contract or external calls to other contracts. And the reason for that is any such side effects made by the modifiers may go unnoticed both by the developers as well as the smart contract security auditors evaluating the security of these contracts. They go unnoticed not only because developers and auditors assume that modifiers don't make side effects, but also because the modified code is typically declared in a different location from the function implementation itself. Recall that the best practice is for the modifiers to be declared in the beginning of the contract and function implementations in the later part of the contract. So as a security check, one should make sure that modifiers declared in contract should not have any side effects, and they should be only enforcing checks on different aspects of the contract. Incorrect modifiers are a security risk. Modifiers should not only implement the correct access control or accounting checks as relevant to the smart contract logic, but they should also execute underscore or revert along all the control flow paths within that modifier. Recall that in the context of Solidity, underscore inlines the function code on which the modifier is applied. So if this does not happen along any particular control flow path within the modifier, then the default value for that function is returned. And this may be unexpected from the context of the caller who called this function on which this modifier is applied. So the security check is to make sure that all the control flow paths within the modifier either execute underscore or revert. Constructor names in Solidity have had security implications historically. If you go back all the way to Solidity compiler version 0.4.22, versions until that version required the use of the contract name as the name of the constructor. And between that version and 0.5.0, one could either use the contract name as a constructor or use the constructor keyword itself. It was only after 0.5.0 that Solidity forced the use of the constructor keyword for constructors. So this flexibility and the use of the contract name as the constructor name has historically caused bugs where the contract name was misspelled, which led to that function not being the constructor but a regular function, and also the flexibility between allowing both the old style and the new style constructor names caused security issues because there was a precedence that was followed if both of them existed. So this constructor naming confusion has been a historical source of bugs in Solidity smart contracts, and this is not a concern anymore. There's a security concern related to void constructors, and what this means is that if a contract derives from other contracts and then it makes calls to the constructors of base contracts, assuming they're implemented, but in fact they are not, then this assumption leads to security implications. So the best practice is for derived contracts to check if the base constructor is actually implemented and remove the call to that constructor if it is not implemented at all. This security pitfall is related to constructors and the checks for any value sent in contract creation transactions triggering those constructors. Typically, if a constructor is not explicitly payable and there is value, ether, that is sent in a contract create transaction that triggers such a constructor, then the constructor reverts that transaction. However, because of a compiler bug, if a contract did not have an explicit constructor, but the contract had a base contract that did define a constructor, then in those cases, it was possible to send ether value in a contract creation transaction that would not cause that revert to happen. And this compiler bug was present all the way from version 0.4.5 to version 0.6.8. This security pitfall is related to the use of delegate call in contracts where the delegate call may be made to an address that is user controlled. Recall that in the case of delegate calls, the calling contract makes a delegate call to a called contract where the called contract executes its logic on the state of the calling contract. So if the address of the called contract is user controlled, then the user may accidentally or maliciously make this delegate call to a malicious contract that can make unauthorized modifications to the state of the calling contract. Therefore, delegate calls should be used with extreme care in contracts, and all precautions should be used to ensure that the destination addresses for such delegate calls are trusted. The reentrancy security pitfall is perhaps unique to smart contracts, where external calls made to contracts can result in what can be thought of as callbacks to the called contract itself. So for example, if there is a contract C1 that makes a call to an external contract C2, where C2 could potentially be untrusted, could be malicious because it is not developed by the same team or within the same project as C1, then that external contract C2 could call back into C1 to the same function that called it or to any other function of C1 that allows such a call. And this could be exploited to do malicious things such as multiple withdrawals or something less harmful such as out of order emission of events. There have been multiple exploits that have taken advantage of this class of reentrancy attacks. Some of them are historical in nature, such as the DAO hack on Ethereum. So this class of security vulnerabilities that is specific to smart contracts really needs to be paid attention to, and the best practice to prevent such reentrancy vulnerabilities from being exploited is to follow what is known as the checks, effects, interactions pattern, or the CEI pattern for short, where the interactions with external potentially untrusted contracts is only made after performing all the checks and all the effects, where effects are nothing but changes to the state of the calling contract, so that any anticipated side effects of interactions with the external contracts are already reflected in the state of the calling contract. So this CEI pattern is recommended as a best practice to be followed in all functions that are making external contract calls, specifically to contract calls that could be malicious because they're untrusted. The other best practice is to use what are known as reentrancy guards. We talked about this in the context of the reentrancy guard library from OpenZeppelin, where a modifier, a non-reentrant modifier is provided, which when applied to specific functions prevents them from being called within a callback. So it avoids any reentrancies to that function itself. This security pitfall is related to the use of ERC 777 standard and the potential for reentrancy vulnerabilities due to the callbacks it supports. Recall that ERC 777 standard is considered as an extension to the ERC20 standard. It's considered as making improvements to it, and one such improvement is the notion of hooks that it supports during token transfers. If such an ERC 777 token contract is potentially malicious, then it could use these hooks to cause reentrancy into the calling contract. So for example, if there's a contract C1 that calls an ERC 777 token contract that is malicious, then that contract could use the hook functionality to cause a reentrancy into the calling contract C1 and take advantage of it, as we just mentioned. The best practice again is to follow the checks effects interaction pattern in the calling contract, and also to consider the use of reentrancy guards. This security pitfall is related to the use of the transfer and the send primitives in Solidity. These primitives were introduced as reentrancy mitigations because they only forward 2300 gas to the called contract, which is typically sufficient only for basic processing, such as emitting a few logs or something even simpler. And this gas is not enough to make a reentrancy call back to the calling contract, which requires more than 2300 gas. So this has been recommended for a long time as a security best practice for preventing reentrancy attacks. However, over time, some of the opcodes have been repriced when it comes to their gas usage. So their gas cost has increased in some of the recent hard forks on Ethereum, and because of that, the use of these primitives that enforce the gas subsidy of 2300 gas could break the contracts, because it might not allow the called contract to even do the basic processing that we just talked about. So the latest security best practice recommendation is to not rely on transfer and send as reentrancy mitigations, but instead to use the low-level call directly that does not have those hard-coded gas limits, and couple that with a CEI pattern or reentrancy guards, or both, for reentrancy mitigation. This security pitfall is related to the notion of what is private data on a blockchain, or the privacy of on-chain data. Recall that state variables in Solidity have a function visibility specifier, and by making this specifier private, such private state variables cannot be read only by other smart contracts on the blockchain. This does not mean that they cannot be read at all and that they are considered private in a confidentiality perspective, because the state of such variables and contracts and transactions in general on the blockchain can be read by anyone on the chain itself or via off-chain interfaces by querying the mempools for transactions or by querying the contract state itself to look at what values such private variables contain. This effectively means that there is really no notion of data being private on the blockchain, and any such data for confidentiality reasons that needs to be private should be encrypted and stored off-chain. This security pitfall is related to pseudo-random number generation on the blockchain within smart contracts applications that require such random numbers. Recall that these values could be influenced to a certain extent by miners who are mining the blocks that contain these values. So if the stakes in those applications using these as sources of randomness is really high, then such actors could use their influence to a certain extent to gain advantage. So this is a risk from randomness that needs to be paid attention to, something to be aware of. And if the stakes are really high for the applications where you desire a much better source of randomness, then there are some alternatives such as the verifiable random function that I would encourage you to learn about. Similar to randomness, the notion of getting the time on chain is also tricky, and often smart contracts resort to using block.timestamp or the block number as sources for inferring the time within the application's logic. Again, what needs to be paid attention to is that this notion of time can be influenced to a certain extent by the miners. There are issues with synchronization across the different blockchain nodes, and there are also aspects of the block times that change by a certain degree over time. This is again a risk that needs to be paid attention to, and there are some alternatives to this using the concept of oracles that I would encourage you to read more about. This security pitfall is related to the notion of overflows and underflows in Solidity smart contracts. This is applicable to any integer arithmetic that is used within the contract, which is very often encountered. And when such arithmetic is used in a way where the increments or decrements to those integer variables are done without checking for the bounds, then they could result in wrapped values where the value exceeds the maximum storage for that integer type, and hence overflows or wraps to the lower end of that type. Or if it's being decremented, it could be decremented below zero, in which case it results in wrapping to the maximum value of that integer type. If those extremely high or extremely low data values resulting because of wrapping are invalid in the application's logic, then it is okay. But if it is not, if it is valid in the application's logic, then this could result in unexpected behavior in the best case, or in the worst case, it could result in some very serious vulnerabilities that can be exploited. And we have seen multiple vulnerabilities and exploits related to overflow and underflow historically. So the recommended best practice is to use the safe math libraries from OpenZeppelin that enforce the overflow and underflow checks during integer arithmetic, or to use the latest Solidity versions greater than or equal to 0.8.0 that introduce checked arithmetic by default. Another security pitfall or best practice related to integer arithmetic is the use of divide before multiply. Solidity integer division might truncate the value of results. Therefore, if division is done before multiplication, then this may result in the loss of precision of the values being computed. So the recommended best practice is to always do the multiplication operations first, followed by any division that is required.